Should I wait? Should I start? Okay.
The time is again we are
Yeah,
already
yeah.
late by.
No, and I will be very quick.
I'll just go outside and see if somebody's there.
Okay. Okay. Hello. I think I will start. I actually will have a very short presentation, and more than a presentation, I hope I can provide some motivation for the topic that I'm working. For one of the topics that I am working on. First of all, well, thank you very much for this opportunity. My name is Cesar. Can you please help me with? My name is Cesar Montalvo, and I am currently I'm a PhD student at Arizona State University. And please, if you have any questions or any comments, just raise your hand and say, no, please. So very quickly, something about me. I'm from Ecuador, and I'm originally an economist. I had the opportunity to do my master's in economics at Iowa State University. Right now I switch to apply mathematics in Arizona State. Further, I will give you some ideas why I'm doing this. But before I started my PhD program, I worked for 9 years in the government of my country. I had the opportunity to be 5 years at the office of the president, because I met this professor when I was an undergrad, and I was a TA for this professor, who eventually became involved in politics. And in year 2007, he ran for presidency, and he became the president of the country. So that's why I got a lot of interest in public policy. And as I mentioned, currently I'm doing my PhD at Arizona State. This is just a picture of our nice program in Arizona State, the MTBI. I hope you can have a chance to get a little bit more about it. And here is where I start my presentation. Well, all of us are modelers. Why modeling? Why should I believe what I'm trying to model? Okay, I think somebody mentioned already this big principle. All models are wrong, but just some are useful. We will see why. George Box in the 70s mentioned this. And very important, what I want to answer, what I want to ask through my research question. Now, why I'm bringing this and why the topic I chose is because you commonly see that models consider average behavior, but commonly we have adaptive agents. We have interactions between agents that are commonly not considered in an average model. And the heterogeneity is something that I want to stress. This is something new, for example, in our models too. And some simple rules, can just change completely the entire behavior. Now, I'm going to focus my presentation in agent-based modeling. To be honest, this is a new area for me. I just explored it since 1 year ago. But I found a powerful, an alternative way to do some modeling. Now, why agent-based modeling? Why not, right? That's the answer. And here are just some ideas. It allows random interactions. We need to provide full information, or try to provide full information. There are some assumptions of perfect rationality, and we can just model, one or millions of agents. Okay, some insights about the program. Okay, this was supposed to be a hands-on workshop, but now for the time, I will just show the initial ones. Yes, well, actually, it's very simple to install. Just if you can also make a search of NetLogo, you can download this program. It's very friendly, as we will see. And this was designed by a professor at Northwestern University. And it's open source, free, which is the most important one. Okay, and it's used widely in economics, biology, physics, chemistry, etc., etc. So let's start with this. Now, just a brief note on installation. Well, I think you can if you are more interested about this, we can speak later, or you can try on your own. Really very friendly. Now, the basic steps. Okay, just consider. We need to consider 4 things. We need to create our environment, our planet. We're going to make a toy planet, and we are going to play with participants in the planet. They are commonly called turtles. I don't know where the name comes from, but agents, whether animals, if we're talking about a predator prey, all of them will be called turtles. We will just give, turtle 1 will be, I don't know, the wolves. Turtle 2 would be the rabbits, something like that. We need to define the dynamics, which is the interactions that they have. Some of them, are the prey. Some of them eat the others, etc. And we will see that NetLogo helps us to analyze emergence behavior. This is probably the most important aspect of NetLogo. And also, it helps us to do repeated experiments. Now, I'm going to focus on these 2 models at the beginning. So please, if you let me open. Well, my program is right here, the NetLogo. And I'm just going to open. And the first thing you do is you get this interface. Okay. Now, it's as I mentioned, I think NetLogo is a very friendly version to do modeling. Now you will see this first part of the interface. Okay, where you can see our planet. Okay, our world, and also some of the graphs that we can put here also, some basic information. I will explain briefly what it means. Now, commonly, NetLogo has, as you can see here, the interface. The second part, which is the info, okay, what this model is, what are the details of the model. So I'm not going to read it, but I'm just going to show it, It says, well, it mentions all the assumptions. Here is actually a Kermack-McKendrick model that we have mentioned in this workshop. And you can have here more details about how it works. Actually, when you will, if you're interested and if you want to construct one of these, you have to, you have to also type and write all the assumptions and all the steps that you need to follow. And secondly, how to use it, etc., etc. This is the second part. And the third part is the coding. Okay, this I know you are professional coders, so this I'm not going to go through every detail, but here is where you start saying, please, I want in my planet of this size. I want that in this world there will be wolves and rabbits. I want the rabbits to be white color, wolves be, I don't know, red color or whatever. And eventually, the interactions. As I mentioned, the people, the animals are called always turtles. And then you eventually detail every interaction among these agents. Okay. So once again, you can go through this. I just want to motivate some of the use of this. But what do I do with this? Okay. I go back to my interface, and this is what I expect to see. Let's start with the model number 1, the basic epidemic model. Okay, it's going to simulate the spread of an infectious disease following the Kermack-McKendrick model. There will be homogeneous mixing, and it will help us to calculate the R0 that we mentioned previously, the average number of new infected individuals. And with this assumption, at the beginning, each individual has a 5% chance of being infected. Okay? And also, the assumptions of stochasticity. I will explain this, where the stochasticity comes from. Okay? So, always the first step, I create always these bottoms setup. So I initialize my planet. So you can see, my initial condition said, please create 100 people. So here's the 100 people, and 5% of them have to be infected. Now, I recognize the infected ones because I gave them a red color. You can put any color that you want. Now, in this world, what I'm going to do through the bottom go, I'm going to put it a little bit slow. Okay, you can regulate the speed of your model, and I'm going to push the go, and you will see that interactions start to happen in this world. Okay, so my agents start to move. The stochasticity comes because they are set to walk one step and then turn to the right, and then and turn, I don't know, any distance, any amount of degrees. So you can see by now everybody's infected or recovered. Recovered, I mean, by the green ones. Okay, the infected, the red ones. And as the interactions go, the nice thing of NetLogo is that it allows me to have the number. Okay, the number and also my measurement of R0. Well, in this case, it's 4.4. It's it's because almost everybody got infected, right? So, and this is one of the nice features of NetLogo. Okay, I don't know if you have seen this before. Probably this is new for you. It was new, very new for me 1 year ago. But once again, as a modeling exercise, and now it is stopped. I mean, if everybody recovered, the program says, please stop. Okay. Now, as a resource for the classroom, this is a powerful tool to show students, first of all, the concept of R0, which is really a beautiful idea. Okay, about how to express epidemics, and also the number and so on. This is, again, there are a lot of tutorials for NetLogo. It's very friendly. And this is basically what I wanted to show. Now, let's try it just one more time, because as your model keeps going, I'm going to make it work again. You can move, and you can say, the infection, the chance that you get infected, it can grow, and you can see that the number of red individuals start to grow immediately as I move this handle from I don't know, I think it was 30 to 75 and so on. So you can also show this. The recovery chance, you can also play with it a little bit. What if people recover very slowly? I don't know, and so on. And then you can see that how the number of infected and non-infected changes as well. Okay. All right. Well, this is the basic one. Okay, I wanted to share this with you. One very important thing of NetLogo, it has a lot of basic models. If we go here to File, we have a library which provides a lot of examples. Now, the examples that I am taking come from this library, curricular models. But as you can see, there are computer science. There are like incredible models, for biology, following the behavior of ants, moths, sunflower, etc., etc. Also for games, for social science, for economics as well. And the next one that I wanted just to share with you is this model which includes travel. See, yep, travel and control. Just the basic assumptions. Now I'm creating this world with two groups. You will see that there are squares and circles. Here there is no the person shape anymore, but they are geographically divided, and this is the nice new feature of this model. There are also contacts, and they get infected, and sick individuals can be isolated. They go home, they go to the hospital, or they can be in quarantine. Okay, also in a hospital, or they just move around. Now, what is the model? I initialize. You can see that this is a little bit more complex. It has more parameters, a lot more parameters. Okay, and there will also, yes, here, the white will be considered an infected, the red infected, green recovered, blue inoculated, and there will be also, as you will see, a yellow person, which represents the health official or the ambulance that takes the infected person and takes it to the hospital. Okay, just to give you an idea. Now, very briefly, let's run this. Again, setup. I think I initialize with 100 on one side. Okay, and now you can picture, I don't know, you can picture this as people from Colombia, people from Venezuela, I don't know, Mexicans, Americans, Pakistan, India, I don't know. Okay. It doesn't tell you anything about the legal status though. And here you can see the ambulance, right? My two yellow individuals, and now set up, and then we go. So as you can see, well, this is very fast actually. Okay, I'm going to decrease the speed. So now you can see that they start to move, but and you will notice that the circles, okay, they don't cross the border. Simple as that, okay. But again, one of the features in my model allows me to travel, okay. So when I activate the travel, now please, I set up again, and when I go, you will notice that the circles start to pass to the other side, right? Does it get closer to the real life? Of course. Does it tell me new stories about my infected populations? Of course. It allows me to, to say a story, and this is it. So you can make it more complicated. You can, I don't know, double the. Yeah, actually, that's one of the questions, right? You can double the number of ambulance. How many more ambulance do I need? So then the populations can control this effectively, and that means public policy. That means money, okay, etc., etc. So, well, this is what I wanted to share with you. I think I'm running out of time. I also wanted to be brief because the best way to learn this is if you sit and then you explore and start to code. Also, it's not difficult, but more than anything, I just wanted to let you know that there is this nice software, very friendly, to help you explain and to help you understand what's going on here. And that's it. Thank you very much. I wanted to, yes, thank very much the Institute. Well, before that, some resources. There is an open agent-based modeling course, and it's run by Arizona State University. And you can also see a lot of courses. There is actually a January, I think is a school in January at Arizona State. You can try this, and there is also, Columbia University has these population health methods, and they also use this extensively. And well, thank you very much to the Institute. I also want to thank the Simon A. Levin, our Center for Modeling, Professor Carlos Castillo, Professor Anuj Mubai. If you have their contacts, please write to them. And the National Science Foundation also because of their support. And thank you very much.
Thank you, Dr. Cesar. So here is our token of appreciation and love. In the audience, if you have any questions, you can ask. If there are no questions, then we'll move on to the next part of the session. So basically, we have oral presentations. We have by actually 4 members. Dr. V. Paparao. So he'll be the first person to present. Comes. Then Dr. Kondal Rao, and then Dr. Narendra, right? Yeah. So you'll be third. Dr. Apparao has not appeared, no? So we are cancelling that. So Dr. Paparao is from JNTU University College, Vijayanagaram. He'll be talking on dynamics of prey-predator model with time delays. Okay, sir, so you are having 15 minutes, so I'll give you a signal after 12 minutes.
Once again, thank you very much for giving this opportunity to talk on my models, which we are already working on prey-predator models extensively. Of course, the morning session we have a good discussion regarding prey-predator models, and we are extending our model with one prey and two predators, where two predators on preying on one prey, and among there is a competition among two predators for a common food on prey. And of course it's a delay differential equation model, where that is integral differential equations we are using to calculate or to accelerate the rich dynamics, where we can identify we are taking two delay kernels. One is called a square memory function, other one is called an exponential memory function. And my research studies in that particular model, rather than explaining more about mathematical component, we are going for some simulation results, where what is the impact of delay while using exponential kernel, while using memory kernel, and what are the similarities we can find with respect to a particular parameters. We are not assuming, actually we are calculating with response to the given mathematical model. Myself, Dr. Ravi Papar, working as assistant professor in Department of Mathematics from JNTU Kakinada University, working under Vizianagaram campus. So actually my paper is consisting of three species. One is with prey and another two predators. And the more impact on a continuous delay is incorporated in the interaction between prey and first predator, and we introducing two kernels. One is already informed that one kernel is square memory and another one is exponential kernel. And we study the global stability. Of course, a lot of mathematical stuff is included there. And of course, meanwhile, I will show how to calculate all these calculations. And I study the delay impact, what actually using numerical computation by taking some parameters of lambda and t. And I compare all this and I can identify the rich dynamics. So the motivation of the work is so long pre-prediction models are extensively studied by Kapoor and all, and delay differential equations by Srihar Rao and all, K. Gopal Swami, very important. And of course, we studied a lot of models, which is prey, predator, mutualism, communalism, and almost all interactions. And presently, I am focused on prey-predators model and the rich dynamics. So this is actually the model which we have, that is N1 is the prey and N2 is the first predator, N3 is the second predator. Both are preying on N1, and there is among the competition which is almost you can find everywhere in this model, but where we are including some delay. So once we are including a delay, and how the system dynamics, what is the impact of the delay on the system dynamics we are studying. So this is my mathematical model, where I can included this. This is a delay parameter, which is called a kernel k1 and k2. This is an interaction coefficient between prey and predator, alpha 1 2 and alpha 2 1. And if you change this k1 and k2, how this dynamics of that entire system will impact, that we are going to study. Of course, the common points is equilibrium is the one point, and the local stability we are studying, and global stability. Apart from this, we are identifying these parameters for the numerical computation, A1, A2, A3, and all these parameters we can calculate from stability point of view. We can approximate those results, and K1 and K2 we are taking, and how you can see the impact, how this K1, K2 plays a rich dynamics with respect to this particular model. So these are the parameters and notations which you can impose that, N1, N2, N3. These are the strengths of prey, predator, and competitor. These are the growth rates. And this is interspecies competition, where yesterday we talk about all. And these are the coefficients, interaction between prey and first predator, and 2, 3, and 3, 2. And of course, we are including the D1, D2, D3. These are called the death rates are also incorporated. And these are called the delay kernels. And this is the nomenclature we are employing. And normally, this is the kernels we are choosing basing on these results. Integral 0 to infinity k1z is equal to 1, and if you take this, this should be less than infinity. By taking k1 of t minus z, and you normalize these equations, and finally if you normalize these equations, the system of 2.1 reduced to 2.3. And you starting solving this equation by equating these three equal to 0, then we got equilibrium state, which is common. And of course, we will find 8 equilibrium points. Out of 8 equilibrium points, I take the coexisting state where 3 population species are existing, that is N1 bar, N2 bar, N3 bar. And these N1 bar, N2 bar, N3 bar are exist provided if all are positive. You can derive conditions that where these conditions, the denominator is greater than 0, numerator is greater than 0, or both are less than 0. So many conditions are there, so that just I include only N1 bar greater than 0, N2 bar greater than 0, N3 bar greater than 0. So you can derive some conditions also. Next, the local stability I can talk about. Constructing a Jacobian function where the variational matrix, I take in the square memory function k1z, k2z is equal to 1 by t, 3 less than 0. And I include by taking convolution theorem, applying the Laplace transform technique, a lot of stuff in mathematics. And I can convert into this Jacobian matrix, and I can find a characteristic equation where b1 I can calculate b2 and all these values. A lot of calculations are including algebraic calculations. And by using Routh-Hurwitz criteria, that I can calculate that b1 greater than 0 and all the 3 denominators are greater than 0, then the system is locally asymptotically stable. Otherwise, the system is unstable or what, destable, whatever you call it. And I can calculate all these calculations, and a lot of calculation. Alpha 1 is also a big value there, and we want to calculate more about this alpha 1, alpha 2, alpha 3. So I can choose one of the choices, alpha 1 less than 0, less than 0, all 3 less than zeros. Then this beta 1 is greater than 0, and all calculations I imposed here. And if all these values are greater than 0, like condition 4.1, 1.5, 1.6, 1.7, all are greater than 0, then my system is globally or asymptotically stable. Otherwise, any of the conditions are failed here, okay, by choosing the particular parameters, then the system is destabilizes. The same I can take for another exponential function where we can use more function. This is called exponential kernel, we can call it as. And we can, so many things are there here, where a power p, u power p by p plus 1 factorial, where p you can run from 0 to infinity. But I avoid that, okay, but only my talk is only for one exponential function, a into e power alpha, and I calculate the Jacobian for this and all the calculations I had. And these are the conclusions or conditions. If all these are positive, then the system is asymptotically stable, because 3 species is somewhat has a complex dynamics. When you compare with 2 by 2, the calculations are little bit easy. Come to 3 by 3, the more computations or more algebraic calculations are involved. So we have 8 equilibrium points. Out of 8 equilibrium points for this system, 4 equilibrium points are stable, but I just enlighten you with respect to these 2 kernels, what are their dynamics. Now, the very important point is global stability. Here, no need to apply for kernel 1 and kernel 2, because it's only one shot where I can construct a Lyapunov function, provided you can identify a suitable Lyapunov function where the derivative of the Lyapunov function is less than 0, that is called a negative definite. Then I can show that that entire system is globally asymptotically stable. So this is, I just estimated, or I construct a Lyapunov function and I calculate a derivative, and using all relations of kernel and everything, I just find, okay, these are all algebraic calculations and assumption, not assumptions actually, these I taken from the mathematical model, and finally I got like this. So this is my mu, where almost some terms are negative by this, so that I can take a minimum value of mu, so that dv by dt is less than 0. Then the system is globally asymptotically stable. Now the very important point we come with, that is a numerical simulation, and all these values are not accidental. Okay, so all these values we are derived from, which are satisfying from equilibrium point, what we shown in the previous slide, that equilibrium points dn by dt is equal to 0. So which is satisfied n1 bar greater than 0, n2 bar, n3 bar, so that I take all, and all interactions like alpha 1 1 1 2 is interaction is lies between 0 and 1. Okay, 0 means there is no interaction between those 2 species, and the interaction is 1. That is an exact interaction, but it may not be possible, so that it's all, I take it in between 0 and 1. At the death rates, okay, there is a one uniform assumption I made, that birth rates are more when you compare with the death rates. Okay, even if you take the death rates are more, you will get another dynamics. Okay, my talk is only just I take all the values of D1, D2, D3, and A1, A2, A3 are here, these are called birth rates or growth rates, where these are called the death rates of the species. Now the normality I choose here, death rates are less when compared with the birth rates. And even you can take it, death rates are more, and what is the dynamics, you can see that whether you will get a quietic nature or whether you will get like limit cycles and everything, you can see inside based on D1, D2, D3, whether you can take it which is greater than your birth rates. This is also one research people are doing. But now I take it the first kernel and I made it the model 2.1 into, by substituting this kernel, and my model becomes 6.1, okay, because that is a numerical simulation, and all these values I substituted here, and I run the simulation, and I take the values for lambda and t for the different simulation values of 10, and I can identify some periodic oscillations, and some species here the second predator is existent, here the first predator is existent because of all the parameters, and these lambda and t or the delay kernels where that is impact is there. So hence I can find a different dynamics here, and here is some oscillatory and asymptotically stable, all those things I put it on the table, and rest I will show the graphs where you can understand and what is the difference between first kernel and the second kernel, or you can take it as what is the impact between the first kernel and second kernel. So now the same, like I can explain, this is exponential because my friend we are going to explain the next topic is Kondalrao is taking this kernel and he derived some results. So I compare this, whether you can square memory or exponential, and what is the impact of the delay with respect to these two kernels. So now I take it this, I will get this lambda is a Laplace function, here you substitute, and I simulate this MATLAB using ODE45 tool, and I derive some results with respect to the lambda and a for the same. I took the same parameters of lambda and a for this kernel and the previous kernel, and I studied. I see some time series plots with respect to the first kernel, and I can see some oscillations you can have with respect to this lambda and with respect to small t. Whereas in the second kernel, if I take suddenly there is an oscillations in first predator population. So there is a difference between the same system with respect to this kernel. This is asymptotically stable and it is neutrally stable. So I studied what is the real dynamics happening with respect to the kernel with respect to the same parameters. So I studied all this. You see, if you see here this same for this kernel and this kernel, and I can identify some results where you can see for this kernel and this kernel almost the results are similar. So this is the rich dynamics where you can identify with respect to the parameters. So the numerical simulation gives much importance where we can see some related results there. So I can plot this, and so these are the some graphs I take already which explained in the previous, so 10, and I can same with respect to phase portraits also I compared here, and finally these are the results where. So finally this is very important where we can struck with this model where we can take the two delay kernels, and of course with you applying the two delay kernels with the same values because the model is okay. So just 1 minute, okay. So this is if you take this kernel and this kernel, and of course the system is asymptotically stable with respect to this particular point. So these 4 different 5 parameters where even the kernel is different, but the delay impact is same. So that dynamics we are studied using this particular model. So of course the Laplace stability and global stability, local stability is common here. So actually one parameter people are choosing for identifying this delay kernel. This is a continuous delay kernel which is very relevant in these prey predator models. Of course you can apply for discrete models also, but I can see the rich dynamics where with the 2 different kernels also I got some parameters where we can encounter with the same stability analysis. And this is my talk with respect to this 1 prey and 2 predator models. And of course these are my some of the references which I use, and thank you, and any questions we have.
Yeah, I have one question. Your model for the first 3 equations, can you just show us? Or anywhere where you have shown the whole model, 3 equations. Yeah, you have one each for N1, N2, N3.
Yes, sir.
And the delay terms you have used only in the first 2 equations.
First and second interaction.
Pardon?
This is the first equation and second equation. Then interaction, that is called Gaussian period actually.
Yeah. So interaction is happening between N1 and N2.
N1 and N2.
there is no interaction between N3 and N1?
Yes, we can have.
But you're not putting the delay
Yes,
there.
yes.
So only between N1 and N2 you're putting delay.
Delay.
Other one, there is no delay.
No delay. And I see how this delay will change my dynamics.
Okay.
You can have, because you can 1.3 and 3.1 also, it's a very beautiful interaction. And even
Right.
have 2, 3
You're
and
not
3.
putting any delay there.
Yes.
Yeah, okay, thank you.
Any questions? Yes.
Have you ever used these models with real data?
Real data we will trying that. That's what validation. Okay, we will get a real data and we will validate that, and we are trying also.
In real life.
This model in real life, actually, this is for a generalized model. We take it. Okay, wherever we have generally that prey-predator models in deforest. Real data we are trying. The real data is ecological data is available, sir. It backs in 1980s or 1987. Last day we see the data, and we try to validate that, because we are working on these particular models, and a few of my friends are working on this. So we want to validate that. Actually, this model is really happening in regular systems, but with respect to particular data, we want to validate, and we will see this how this dynamics will work out. That's what we are point out, and we are trying to first study and validate this data, because unless there is no validation.
Because, for example, in Portugal, we always have, every year we have the same problem.
Yes.
At least at the 10 years ago, we always have the same problem. We eat during the summer sardines. Do you know what is a sardine? It's a fish, small fish.
Yes.
Well, it's very common in Portugal. So, but sardine, it's a problem every year. Yeah. We don't have sardine in sufficient number for the Portuguese people. And one of the problems is the preyers.
Yes.
You know, which the main predator is the man. But some boats have sensors that can count the numbers of sardines and the predators, and I think some researchers are using this kind of models, stochastic equations, differential equations, to predict the number of fish. Yeah. Okay.
That's what we are working.
But anyway, I think you increase the visibility of your work if you one day have real data.
Yes.
That's why I made this comment. It's just a comment, okay?
Okay, sir. We will take it as...
it's a nice work.
Okay, thank you, sir. Thank you very much.
Any more questions? Okay, sir. Thank you so much. It was a crisp presentation. So I'll call the next person. So next speaker is Dr. Kondal Rao from Vidya Jyoti Institute of Technology. He's speaking on dynamical systems of 3 species, amenicalism model with time delay. So again, sir, I will give you an indication after 12 minutes. Thank you.
Om Sairam. Andarki namaskaram andi. This is Kondal Rao from Vidya Jyoti Institute of Technology. I'm Assistant Professor of Mathematics, and recently I submitted my PhD under the esteemed guidance of Dr. K. Lakshman sir. So now my talk is a dynamical system of 3 species, amenicalism model with the time delay. The present model is devoted to analytical study of 3 species in ecological model, which first species amenicol on the second species amenicol on the third species. Here first and third species are neutral. Here first species and third species are neutral to each other. We introduce the time delay between the interaction of first and second species and second and third species. All possible equilibrium points of model are identified, and the stability for each case is discussed, and the global stability is discussed by constructing a suitable Lyapunov function. Further, exact solutions of perturbed equations have been derived. The stability analysis is supported by numerical simulations using MATLAB. Some of the keywords I given here: emmensolism, time delay, equilibrium points, Lyapunov function. Emmensolism is a ecological interaction between the two species, two organisms. One organism is affected on harming the other organism without getting any benefit or loss. So other one is getting loss. So harming the other one without getting any benefit or loss. So example for emmensolism is a pollution caused by automobiles, electricity generating stations, or metals often cause severe damage of plants in the affected area, whereas humans receive no direct benefit from this relationship. From this, we took the model actually that humans are harming humans without getting any benefit by air pollution. We are harming the trees, and from the tall trees, sometimes because of tall trees, the small trees are getting lost. So they are using that. We've derived one model. Here, the basic model equations for the system of interacting species is given by 2.1. First species is harming the second species. Second one is harming the third species without getting any benefit. Here, we introduce the time delay between the first and second species interaction, second and third species. So we normalize the equations. After we get that equation 2.4, as previous my seniors or Paparos are explained. So same process we applied here. So some of the notations: N1, N2, N3 are the growth rate of the population of the first, second, and third species. A1, A2, A3 are growth rate of the natural growth rate of first and second and third species. Alpha I, rate of decrease of first and second and third species due to internal competitions. Alpha 2, the rate of decrease of the second species due to attacks of the first species. Alpha 3, is the rate of decrease of third species due to attacks of third species, second species. N1, N2, N3 are non-negative parameters we are going to take. That is a condition we are assuming, we are taking that here. Equilibrium points. For the system under investigation, 8 equilibrium points are identified. They are given below. The equilibrium points are identified by giving that dni by dt equal to 0. All equilibrium points are classified below. Fully washed out state, all three species are washed out state, given by 3.1, and first and second species washed out state given by 3.2. Here A3 by alpha 3 is the carrying capacity. First and third species washed out state given by 3.3, and second and third species washed out state given by 3.4. Only first species washed out state given by 3.5. Here the state is exist if I3 alpha T2 minus A2 alpha 3T greater than 0. Only second species washed out state given by 3.7, and only third species washed out state given by 3.8. The state is exist only when the 3.9 condition satisfying, and the last one is coexisting state or normal steady state. The state given by 3.10, and the state would exist only when 3.11 condition satisfied. Out of these all cases, by assuming that we assume we have that nonlinear model equation. So to convert into linearization, we assume that perturbation, that small perturbation U1, U2, U3, that quasi-linearization we did that N1 equal to N1 bar plus U1, N2 equal to N2 bar plus U2, N3 equal to N3 bar plus C3. And after linearization, we get du by dt equal to AU, where A given by 4.2 and U is 4.3. The characteristic equation for this system is A minus lambda, data of A minus lambda equal to 0. The equilibrium state is stable when the roots of the equation 4.4, the characteristic equation, are negative if they are real or have negative real parts if they are complex. In the present model, first E1 for equilibrium state 1, 2, 3, 4, 5 and 6, 5 are founded unstable, and hence we discuss the stability of E6, E7 and E8. That is the stability of only second species existing state. That is linearized equations for the existence of first and second species are given by 4.1.1. The characteristic equation of that linearized state given by 4.1.2. And the eigenvalues of this state here, lambda 1 and lambda 3 are negative clearly. After finding that, we get lambda 2 is also negative if the condition satisfied 4.1.4. Hence, the equilibrium state is conditionally asymptotically stable if the condition that alpha A2 is less than alpha 2 1 and 1 bar. The solution of the paradoxical equation given by 4.1.6. Here S2, then that given that stability of the only third species existing state, the linearity equations for the equilibrium state are given by 4.2.1. The Castic equation for the equilibrium state given by 4.2.2, and the eigenvalues here lambda 1 is clearly negative and lambda 2, lambda 3 are negative if it's satisfying that that condition A2 is less than 2 alpha to N2 bar plus alpha to 1 N1 bar, and A3 is less than alpha 3 to N2 bar, that is 4.2.4 conditions satisfied. The system is in the equilibrium state is conditionally asymptotically conditionally stable and coexisting state. Without introducing the delay, the coexisting state is like asymptotically stable, but once introducing the delay kernel, then we get this state also conditionally asymptotically stable if it's satisfying the 4.2.4 condition. And that is local stability. Now we are moving to global stability of the system. The system is globally stable at the coexisting state. Right. We consider the Lyapunov function 5.1. Here N1, N2, N3 not equal to 0. Differentiating the equation with respect to t and simplify that we get 5.2. After simplification we get after simplification we get dV by dt is less than 0 clearly, and the system is globally asymptotically stable at the positive equilibrium point. That is, all three species exist state, that coexisting state. Numerical examples. The system of equations 2.4 are simulated using MATLAB using OD45. Example 1. Here we took that some values of parameters A1, A2, A3 values. As Paparo sir said that in between 0 to 1, we took that values by satisfying the condition of N1, N2, N3 greater than 0, equilibrium states N1 bar, N2 bar, N3 bar greater than 0. Here figure 6.1.1a shows the time series analysis of the model 2.4 is stable system with fixed equilibrium point converging to E of 1.9, 0.08, 0.30. The phase portrait of the system is shown in the figure 6.1.1b. Let us assume that that's stable, that system without delay. Let us assume the delay kernel, the above model. I am taking that exponential delay k of lambda equal to 4 minus alpha lambda, alpha greater than 0. For different values of alpha, the system dynamics is studied and placed in the following table. Figure A shows the time series analysis of the model 2.4, and figure B shows the phase portrait of the model 2.4. Here, for different kernels, for alpha values, we took that if alpha is 0.005, the second species existing, the system is stable under converging the equilibrium point to given the T of 1.9, 0.00, 0.33. And when we increase that alpha value 0.05, again the second species existing. And if we increase the alpha value 0.5, the system is stable and converging to fixed equilibrium point. Similarly, we verified for up to alpha value 100. That graph shows that 6.1 point alpha is 0.005 and alpha is 0.0005, alpha equal 0.5, alpha equal to 1.5 up to alpha equal 100. As an delay kernel value alpha increases, the growth rate of second and third species are slightly increasing. The system is stable and delay further stabilize the system for the above mentioned parametric values. Observations from the first example. The parameters for the model are identified, shows the stable system and the impact delay parameter alpha as ranges from 0.005 to 0.05. The second is washed out state, slightly increases in the third species population and first species population stabilizes, and the system is being stable. As alpha value is ranges from 1.5 to 100, the second and third species population are slightly increasing from zeros. Hence, the delay is having slow impact in the population growth rates of the second and third species. No variation in the first species population growth, even though the delay is imposed. Example 2. again, I took the different values of that A1, A2, A3, alpha 1 interacting coefficients. The system dynamics with above parameter values without the delay argument is shown the graphs of 6.2.1a and 6.2.1b. The figure 6.2.1a shows the time series analysis for model 2.4 is a stable system with the fixed equilibrium point converging to that equilibrium point 1.11, 1.23, 2.3. For the phase plotted for the system is shown in the figure 6.2.1.b. For the different delay kernel alpha, so the system dynamics is studied and placed in the following table. Again, here I took that alpha values, kernel value, I changed 0.005, 0.05. We verified that if alpha is 0.005, the second species exists, there is a significant growth in the third species, the system is stable and converging to equilibrium point. Similarly, alpha equal to 0.05, also the second species existed, and alpha is 0.5, the system is stable and converging to fixed equilibrium point. So this alpha equal to 100, the system is stable and converging to fixed equilibrium point. The graphs what I have that alpha, I verified that for alpha equal to 0.05, 0.05, different graphs. And from the second example, the parameters for the model are identified shows the stable system and the impact delay parameter alpha. As the alpha ranges from again 0.005 to 0.05, second species again was state slightly increases in the third species population and first population stabilize and the system is being stable. As alpha value is 0.5 to 1.5, the second species population is increasing and the third species population is slightly decreasing. Hence, the delay is having so impact in the population growth rates of second and third species. As alpha value is ranges from 1.5 to 100, the second and third species population is increasing. Hence, the delay is having slow impact in the population growth rates of second and third species. No variation in the first species population growth even though delay is imposed. Conclusion that in this present investigation we studied again three species ecological model in which first species MNSol and second species MNSol and third species. In first and third species are notally each other. Here first species and third species notally each other. The time delay is introduced between the first and second species, second and third species. All possible equilibrium points are identified. Out of this only second species was out state and only third species was out state and coexisting state are conditionally asymptotically stable. The impact delay is studied by choosing suitable parameters in support of stability analysis using MATLAB simulation. Two examples are chosen for analysis and detailed investigation with results is shown in the table 1 and 2. The results are compared with the different delay arguments of model with the system without delay arguments. The delay argument further stabilizes the system. In two examples, the system is asymptotically stable. Even we employ the delay kernel, the system will exhibit the same nature. Hence, the delay arguments further stabilize the system. Some of the references I used here. Thank you.
Thank you, sir. Any questions? If there are no questions, we'll go to the next speaker. Thank you, sir. So the next speaker is Dr. Narendra. His talk is on progression dynamics of chikungunya, dengue, and Zika virus infection with optimum control measures. He is from Central University, New Delhi. So again, I will give you an indication after 12 minutes.
Om Sai Ram. Good evening, everyone. Myself, Narendra Kumar. So, the title of my presentation is Progression Dynamics of Chikungunya, Dengue, and Zika virus infection with optimal control measures. So, Aedes aegypti is known as the common vector to transmit the disease chikungunya, dengue, and Zika for all three diseases. So in present article, we discuss the dynamics modeling of these three diseases through the compartmental mathematical modeling in the presence of the mosquitoes. After the theoretical analysis, the model is fitted with the real data of these 3 diseases obtained from the Mexico City during the 2015-16 outbreak. Some control measures are assumed to prevent the infection in the given population, and the effect of these control measures also discussed on the progression of the infection. So these are some assumptions in the model. We assume the homogeneous mixing of the population for the human as well as for the mosquitoes. It means all the individuals had the equal probability of occurring the infection. So second one is the total population of the human is always constant, and population of the mosquito is always constant. The model does not consider the human-to-human transmission and via the sexual transmission, mother to fetus, and other blood transmission, etc. The model does not consider the mosquito-to-mosquito transmission as well, and the model does not consider the recovery of the mosquitoes because the lifespan of the mosquito is very less in comparison of the infection for these diseases. We use the SEIR structure for the host, means human, and SEIR model for the vectors. We prefer the SEIR model of the SIR since it also considers the latent period of the disease, because latent period is important period for this type of infection diseases. The model different categories of the human and mosquito are defined. So susceptible host are defined by the SH, exposed EH, and all these are explained in this compartmental model. So SH is the susceptible human, exposed human, IH is the infected human, recovered human, and these are the susceptible vectors, exposed vector, infected vector, and these dotted lines represents the transmission of the infection from infected mosquito to human and infected human to mosquitoes. And μ is the death rate and birth rate, as we have taken as the population of the mosquito is constant, so we have taken the both as the same. Birth rate and death rate are the same, and there is no birth and death rate is considered for the human population. This is considered because the lifespan is very small, so we include this one, but the lifespan of the human is very large in comparison of this duration of the infection. So we discussed these alpha H is the rate from susceptible to exposed, beta is the exposed to infection, gamma is the infection to recovery rate. Similarly, alpha B is the rate for susceptible to exposed, and beta B is the exposed to infected. So if we convert this model into the mathematical framework, we will get this model. And there is the product of the SH and SV, because only SH and SV, and here is the IH and SV, because transmission is from infected mosquito to susceptible human, and infected human to susceptible mosquitoes. So we also find some equilibrium point for this model. So these are the equilibrium points, and in particular we also find out the disease-free equilibrium point and endemic equilibrium point. After this, we discuss the reproduction number, which can be treated as the expected numbers of the infection in the second stage produced by a single infection, while whole population is treated as the susceptible. So for this, we discuss the linearized subsystem at the infection-free stage, and some calculation is done. We did some calculation to find out this R0, and we calculate the transmission matrix, transition matrices, and we computed the generation matrix G. That will be the minus TV inverse. So the eigenvalues of the G is this, which will be the basic reproduction number is the spectral radius of G, and we will get the final expression for the R0. So model under controlling factors. So there are different types of controlling factor. We discuss only two main factors, which is the isolation of the exposed and infected human, And these are represented by the epsilon 1 and epsilon 2 respectively, and self-protection of the susceptible human, and that is represented by the tau. So in the previous model, these terms are added. 1 minus tau means self-protection, and this epsilon 1 EH, epsilon 2 EH, these are due to the isolation in the exposure infected human. And in this differential equation, this will be the RH. By mistake, it is a printing mistake. So DIEH, this is the EH, IH, and that will be the DRH. So this is the sum of epsilon 1 EH plus epsilon 2 IH. So we also computed the control reproduction number for this model in the similar fashion, and we get this expression for the control reproduction number. So this will be the function of the epsilon 1, epsilon 2, as well as tau also in this expression. So optimum control. So to find the optimum control, we consider the cost function, and we want to optimum this cost function. So these exposed only we consider the control measures on the human population only, not on mosquito population. So this is the EH, IH, tau, epsilon 1, epsilon 2. So we find the Lagrange equations, Hamilton equation for this one, L plus sigma lambda I Zi, where lambda I are the adjoint functions, and these are the P is as taken as this and U is taken as this. So then if P star and U star is the solution of the problem, then we use the Pentarian maximum principle, and the necessary conditions are these by that principle, and if we apply these necessary conditions, then we will get this expression for tau star, epsilon 1 star, epsilon 2 star. So these are the expressions. So this will be the function of the time as well. So parameterization is a crucial step in this modeling. The value of some parameters are taken from the previous literature, and some are estimated through the SimBiology toolbox in MATLAB, which use the least square method. We take the data for 3 diseases taken from the WHO website during the 2015-16 outbreak in the Mexico City, and the data was taken for 44 epidemiological weeks, 42 of the 2015 to 33 weeks of the 2016. And on the these data which are the estimated and taken from the previous literature, we calculate the R0 for these 3 diseases. For R0 is for chikungunya is this, and dengue virus is this, and Zika B is this, at the parameter values which are taken. This is the data visualization which we have taken from the WHO website, and these are the some simulation results. So this is the actual one, dotted is the actual one, and this is the estimated by the model. This is for the chikungunya infection. Similarly, we did for the dengue infection, dotted is for the actual, and these are the estimated. Similarly, for the Zika infection we did, and these are the some simulations for the chikungunya virus, and taking the variables epsilon is 0 and tau is 0, means we have taken the reproduction number and epsilon. As we know, the reproduction number is greater than 1, then infection will invade, otherwise not. So we can see from the graph 0.8 something will be a crucial parameter. The value of the epsilon 1 will be a crucial parameter. If these are the if these are the zeros, then infection can be stopped if the epsilon 1 is greater than this one. Similarly, other parameters simulation can be done, and this is for the if tau is 0 and epsilon 2, so we will get a 3-dimensional figure. So we can find the other simulations for dengue in similar pattern, and we can find out the cutoff values for other parameters as well. And these are the Zika B virus. And some actually we are in process of doing this work, and work is not completed, and some simulations are left based on the optimal control. And hopefully we will complete in few days or few weeks. So the progression dynamics of the viral infection using mathematical model has been investigated for during an outbreak. We also evaluate the effect of the different parameter on the transmission of the infection in a given population. So, and implementation of such model can be used to predict the disease progression. And the prediction of these model can be improved using the data from climatic conditions, vector details, and clinical parameters for evaluation of the outbreak. So my acknowledgement to the CIF Jamia Millia Islamia for the travel support and under the DST Percy grant, and also thanks to the SERP for the other support. And my thanks, these are some references. Thank you, and I am very thankful for the organization committee to provide me the time to present my work. And thanks to my guide also, Dr. Robbins, to give me the opportunity and confidence to present my work. Thank you very much. Any suggestion, questions are invited.
So if there are no questions, then we will conclude the session. Okay, thank you, Narendra Kumar.